Thank you for the introduction. I'm Hong Zizhu from Shanghai Jiao Tong University, and I'm glad to introduce our work here. The title is HyperSight. We're going to use the Dao camera on a smartphone to sense an object in a far range. So this is a joint work with Donghua University and University of Texas at Austin. So nowadays we may say more smartphones are carried with Dao cameras or even more cameras, right? So those smartphones have the potential to sense the 3D coordinate information, including the depth information of an object. Okay, so that information can be of great interest, probably in the future apps. So let me first introduce the basic model of a camera. We use the Pinhole model of the camera. So a general model can be characterized by a simple pinhole camera. Assume this is the length of the camera, and then you will have a sensor, or CMOS sensor. We call it image plane. So we have an optical axis, and this is a focal length. And a physical point in the physical world can be projected through the pinhole and projected on the image plane, which will be the point Q. Okay. So for the ease of representation, we will depict a virtual image plane in front of the pinhole. Okay, so with this model, you can calculate the coordinates in the image plane in pixels, so X and Y. So now if you have two cameras or Dao cameras, what we can do? Now this is one camera, for example, the left camera of your smartphone, and this is the right camera of your smartphone. So, and the distance between the two cameras we call is baseline of the Dao camera. And then if there is a physical point Q in the physical world, it will be projected into the two virtual image planes. And then you can find out the distance or the difference between the point on the left image plane and on the right image plane. And we call the difference the disparity. Okay, so with this disparity, that is the XL minus XR, then you can calculate the depth information Z, right? Okay. So if you use the native Dao camera on your smartphone to measure something, we have some problem. We call it near-far diversity phenomenon. So that means the stereo vision system have different depth resolution for objects in different range. Okay, that means the further the object is, the smaller the disparity you will see on those two Dao cameras. And because of the rounding errors, because you are going to measure those coordinates in pixels, there must be some rounding errors. So the near-far diversity phenomenon is more severe for the stereo vision system with a short baseline. That is the case usually you will see on the smartphone. Because, for example, here, this is an example. The Dao camera on the smartphone normally is around separate about 1 or 2 centimeters. So this is a very short baseline. So we do experiment. If you use these Dao cameras to directly measure the depth information of object in different range, for example, in 1 meter, or 3 meters away, 5 meters away, or 7 meters away, you will get different depth estimation errors. So this is a CDF, or errors. Okay, so how to deal with this problem? This is the core idea of the HyperSight. We're trying to form a virtual long baseline stereo vision system by sliding the phone in the air. And then we need to also continuously perceive how the phone transforms during you slide you're doing the operation. So here is an example. For example, you're holding your phone and you can see near objects, and you can see also a target object which is very far. So we're going to use this nearby object. We slide the phone, and during this slide, those two positions or the whole positions, you will see the same nearby objects. And then you can calculate or you can perceive the transform from one point to another point. This is the rotation and translation, okay, so R1 and T1. And so on and so forth. You can see another nearby object, and you can perceive another transformation, which represent in R2 and T2. And then you will see another object. You get R3, T3. And then since you have already got R1, T1, R2, T2, and R3, T3, and then you can know what is the transformation from the starting point to the end point. Okay, so in that case, you can form a virtual long baseline. You can see here the baseline is in long, right? So in that case, we can use those information to further perceive the depth of the far target object. Okay, so this is the basic idea of HyperSight. So the design of the HyperSight has several components. First, we will need to do offline stereo calibration because we need this process to learn the parameters of the cameras, DAO cameras. That includes intrinsic parameters, extrinsic parameters, also lens distortions. And after that, we'll do image pre-processing, which will transfer the original images into in grayscale, and then we'll do undistortion, and then we'll try to extract all the feature points, or we use the SIFT algorithm to get the SIFT key points or feature points. Okay. And then we'll do transformation position. We try to estimate how the phone is moved in the air. So we will find in common key points or feature points in images before and after the move. Okay. And then we use those common key points, to calculate the 3D coordinates of these points. And with those 3D coordinates, and we can estimate the translation Ti and rotation Ri. Okay. So we will splicing all these translations and rotations, so finally we get the whole movement, and use that to estimate the depth of far target. So for the stereo calibration, we adopt the classic single camera calibration approach. And in practice, we use a 8x9 chessboard and take 20 images. And we also adopted the SIFT algorithm to identify key points. Okay. So after that, we have several key observations. Is from the previous introduction, you will see the depth estimation error can be reduced if I can prolong the baseline. So as long as you can get, okay, that's what you're trying to do. So what we do here, if this Z is the true depth and Z prime is the estimate depth, so we can analyze what is the error, where they come from. So if it comes from the, because the rounding error of the disparity measured in pixels. So you can see here. So this is given the depth Z, and if you increase the baseline B, then you will minimize the error here. So the suggestion is here, you should try to slide the phone as long as you can. Okay. And we have another observation. The phone transformation can be actually estimated only when sufficient common nearby key points can be seen before and after the move. So that means if you move too far away, the number of the common key points will reduce, okay, because the overlapping area is reducing. So in that case, it also suggests to see sufficient number of common nearby key points, the DAO camera should not be slide too far. So they contradict with each other, observation 1 and observation 2. So what we do here is we're going to segment the slide into small segments. Okay, so we will estimate each segment, and then we will splice all the segments together so that we get to form a long slide. Okay. So how to do this? We first to estimate how long we are going to slide. So this can be estimated with, we first do the depth estimation with the first with a native dial camera to do the calculation or estimate the depth z prime, and then we given a threshold alpha, we require that the depth estimation error should be less than alpha. Then we're using this to calculate how far we should slide. Okay, this is a rough estimate. And then the slide is automatically segmented until the number of the common nearby key points in this segment is less than another threshold. Okay, so we try to segment, we try to find the longest segment, unless if you move a little bit more far, the number of common key points will less than this delta. Okay, so that we will try to use a long segment. So after that, we can estimate each subtransformation or segments. Okay. After that, we're going to splicing all the transformation. We get the total or the whole R and the whole translation T. Okay. So I'm going to introduce the performance evaluation. And the settings, we do evaluation in both our laboratory and 2 real-world indoor environments. Okay. And we also include 10 volunteers as the operator to run the HyperSight. And the ground truth is measured with a laser ranger. Okay. We measure the distance from the operator to the target, and actually the front surface of the target, because probably the target will also have some depth. And for HyperSight, we implement HyperSight on Google Pixel 3, and we also compare with the following 4 methods, which is the native short baseline stereo vision. We use here we get a dual camera module, and the baseline can be changed, range from 2.5 cm to 20.5 cm. Okay, so they will give 2 methods to compare. One is the short baseline stereo vision and long baseline stereo vision. And we also compare with the Measure app you can find on the iPhone or iPad. Okay. We also compare with the OSB SLAM 2, which is also a real-time SLAM system that computes the camera trajectory as introduced in previous presentation. So we first examine the effectiveness of the 2 threshold alpha and delta. And empirically, we found the estimation error will reach the minimum when alpha is set to 2%, and when delta is set to 700 common nearby key points. Okay. And we also examine what's the impact on nearby objects, because the nearby objects are essential for the HyperSight, because we need the nearby objects to estimate the transformation of each slide. So if I don't have nearby objects, HyperSight cannot work. Okay, so we further to look at the impact of nearby objects. Here we examine the number of key points found on the nearby objects. If the number of key points reduced to a certain level, for example, less than 50 key points, I guess the HyperSight will not work. Okay. But if you can see more nearby objects, or you can see more key points on the nearby objects, HyperSight works well. You can see here, this is a final estimation error. And we conduct the real-world experiments in the 2 indoor environments. One is coffee shop, another is supermarket. And we also compare with all the methods. To be fair, we set the resolution of all images to this resolution, because we use the dual module camera, and also with the smartphone, they have different resolutions. And we random choose target and change the facing direction for 10 times for each target. And we measure the performance of HyperSight, and the DAO camera with a short baseline and long baseline. Okay, you can see that HyperSight can achieve very low errors, about 2.4% and 4.2 and 7.7% with a precision of 90% at a distance of 5, 6, and 7 meters respectively. Okay, so this distance is the distance from the operator to the target object. Similarly, we also compare HyperSight with Measure and with the ORB SLAM 2. Okay. So here I will conclude my work. So the HyperSight is designed to overcome the low accuracy issue or using the native short baseline DAO cameras to range a far or distant object. So HyperSight is also implemented as a software on the COTS DAO camera devices. Okay. But HyperSight also has several limitations. First, HyperSight will need to see nearby objects in order to track the movement of the phone. Okay, this is one major limitation. Another limitation is HyperSight fits best in static scenarios. Okay, where the target and most objects they are not moving. Okay. Last limitation is that HyperSight also needs both the nearby objects and far objects to have sufficient key points or the feature points so that they can track. If this is a problem, that if you have in the background or the nearby objects, they have plain color or textures, HyperSight will also fail. Okay, so that's all. Thank you for listening.